in one dimension, if you want to describe motion quantitatively, we consider the motion to be along an x-axis. And x-axis is just a number line. The parameter is called x, and the unit is in meters usually, or it might be something else. It depends on the situation. It's 1 meter, 2 meter, 3 meter, and this side is -1 meter, and so forth. And the object is going along this straight line because it is one-dimensional motion. And wherever the object is, for example, if it is here, we read where the position of the object is. We say that the object is at 2.5 meters, for example. We say x equals to 2.5 meters in this case. And because the object is now going along this line, and this x-axis is right parallel to it. So this is the position. So position is just a number. And then we define displacement. Displacement from one point to another, if x is equal to xi, and then later if x is equal to x final, well, x initial, x final, then displacement is denoted by delta x, is defined by x final minus x initial. Displacement can be positive or negative. It depends on whether x final is to the right of the x initial or to the left. If the object is going to the right, the displacement is positive. If going to the left, the displacement is negative. After displacement, we define average velocity. Average velocity is simply defined by displacement divided by the time. T and x. At time t1, the object is at x1. At time t2, the object is at x2. Or you can say t initial, t final, x initial, x final. If that's the case, we define the average velocity, we denote it by v and a bar over it. Sometimes we denote by that, sometimes we say v average. Defined by just displacement divided by time, or delta x over delta t, or x2 minus x1 divided by t2 minus t1. This is the definition of average velocity. So because this is displacement over time, t2 is usually larger than t1 because it's time passing by, it always goes forward. x2 and minus x1 can be positive or negative. Therefore, average velocity can be positive or negative, depending on whether the object has gone to the right or to the left. Usually we take the right direction as positive, the left direction as negative. So that, of course, depends on our coordinate axis, which is optional. Usually we take it to the right as positive. We also define average speed. Average speed is a bit different. You remember from high school?
Is it the absolute value or velocity?
Not for average.
Oh, not for average.
Not for average. That is true for instantaneous velocity and speed. We're going to see that. But average speed is the total distance traveled divided by the time. What is the difference between these? Think about the difference. We denote it by S with the bar over it because it's the average. So distance traveled divided by time. So what is the difference between this and that? Yes?
Displacement is like how far away you are from original position, whereas the distance traveled is like you can be moving in any path. Like you can cross your initial path, but it would just keep going up and up and up. But
yes,
like,
that's right.
I could be going like this and stop here, and then that'd be
Yes, exactly. Let me give you a simple example. If I move from here go like 7 meters this way, and then come back 4 meters, my displacement is what? 3 meters, right? Of course, in this case, negative 3 meters, right? But my total path is how much? I went 7 and then came back 4. That's 11 meters, right? So it can be different. In displacement, we don't care what's going on in between. But for distance travel, of course, depends on how you get from point A to point B. So in that sense, you see that the average speed is not the magnitude of average velocity. We're going to have more numerical examples later. By the way, as I said, the average velocity can be positive or negative, but because distance traveled is always positive, average speed is always positive. Speed cannot be negative. Speed is how fast the object moves. Instantaneous velocity is defined as the average velocity in a very, very short time interval. It's short enough so that nothing exciting happens during that time interval. So mathematically, we define this by v. We say it's limit of delta x over delta t as delta t goes to 0. And if you remember from calculus, does it ring a bell? What is that?
Difference quotient. Well,
difference
dx dt.
dx dt, yes, the derivative, right? So dx over dt means that the velocity, instantaneous velocity, is the derivative of the position with respect to time. So for example, if you have position as a function of time, given like an expression, you want the velocity, you take the derivative of that, you get another expression that tells you a velocity at any time. Or if you have just a graph, we will talk about how to get the instantaneous velocity. And now, instantaneous speed is just the magnitude of instantaneous velocity, as you said. Because during this small time interval, nothing exciting happens, so the object is going only in one direction. In that case, average speed and average velocity have the same magnitude. But average speed is just positive. So the instantaneous speed is just magnitude of instantaneous velocity. But we cannot say the same thing for the average speed and average velocity. That is the case if the object only goes in one direction, doesn't turn around. And then we talk about average acceleration. Average acceleration is denoted by A average with bar over it. And that is delta V over delta T, which is V final minus V initial divided by T final minus T initial. Instantaneous acceleration defined by limit of average acceleration when delta T goes to 0. Limit of delta V over delta T as delta T goes to 0, which is dV over dt means derivative of velocity with respect to time, and because velocity is derivative of position with respect to time, this becomes second derivative of position with respect to time. This is briefly all the definitions that we have for one-dimensional motion. I didn't talk about the units. The unit of velocity, meters per second. Unit of acceleration is meters per second, which is meters per second squared. Now, of course, these are the standard units. You have other units, like for the speed, you know, you have mile per hour, kilometers per hour, and any other thing. These are our original definitions. Then we talk about what happens when acceleration is constant. So when acceleration is constant, then the instantaneous acceleration and average acceleration are the same. So we can just say acceleration is delta v over delta t, or v final minus v initial divided by t final minus t initial. Usually we change this equation to show it a different way. For example, writing final velocity in terms of acceleration and time. And if we do that, we can cross multiply this, get v final minus v initial equal to a times t final minus t initial. But then this has a lot of indices and is not very pretty to look at. So we simplify the notation a little bit so that these equations look simpler. So we use a convention. The convention is that we usually start the time at the beginning of the problem. So it means Ti is usually taken to be 0. So Ti is 0, and because you don't have Ti, T final is simply taken to be just T. Right? So because we don't have Ti then, we just call T final T, because we don't have 2 times to be confused about. That simplifies this equation. And also, we call V initial V with subscript 0. So Vi, we call it just V naught, or V0. And for V final, we just call it V. Because for I, we have index 0, for final, just without index. That makes it simpler. And also for X initial, we call it X naught, and X final, we call it just X. And that's not here, but it will show up. So these are our conventions. Remember that, because it's very important. And in that language, this equation becomes V minus V naught equal to A times T. V becomes V naught plus AT. So this is for constant acceleration motion. So from here, everything I'm saying is for constant acceleration. If the acceleration changes somehow, you cannot use these equations. And then we have V equal to dx over dt. So we have dx over dt equal to V, but V is V naught plus AT. Dx, if you want to actually solve this equation for x, dx is V dt, and then you integrate over dx, and equal to integrate V dt. And here, the integral here from x naught to x, and this will be from 0 to t. Right? Because initial situation, t is 0, x is x naught. Final situation is t equal to t and x equal to x. And sometimes you got to t1 and t2 if you want. In general, we have t1 to t2. But here, you see, this one becomes just x minus x naught, right? Integral of dx is x. Put this upper limit minus the lower limit. It becomes x minus x naught, which is displacement equal to integral of v dt. This is the statement that usually they say the area under the graph of velocity versus time is equal to displacement. Right? Because sometimes if v becomes negative, it should be signed area, basically. But you know what we mean by integral. Now I want to go further and calculate actually this integral. The v is v naught plus at. So if you write x minus x naught equal to integral from 0 to t of v naught plus at dt, then x minus x naught equal to v naught t plus 1/2 a t squared evaluated between 0 and t. So for 0 it's all 0, for t is the same thing. So we can just say, when we move this x over, x becomes x naught plus v naught t plus 1/2 a t squared, which is our second equation for constant acceleration motion. This is our first equation. This is our second equation. For constant acceleration motion, because velocity changes linearly, the average velocity between t1 and t2, let's say, is equal to the average of initial and final velocity. So the average velocity is equal to, the average is equal to v1 plus v2 divided by 2. Say x minus x naught is equal to v initial plus v final divided by 2 times t in our notation. But that's exactly displacement equal to average velocity times time, right? Or average velocity is displacement over time. This is another equation that we have. And this is another side comment, that average velocity is equal to average of the initial and final velocities. And that's because acceleration is constant. And we have that. Okay, now if we combine this equation with that equation, we get another equation. We want to eliminate time between these two. This equation gives you t equal to v minus v naught divided by a. The other equation gives you t equal to 2 times x minus x naught over v plus v naught. And then this is t, we can put these together. V minus v naught over a should be equal to 2x minus x naught over v plus v naught. Then if you cross multiply, you get v minus v naught, v plus v naught, get v squared minus v naught squared, v squared minus v naught squared, equal to 2a times x minus x naught. This is our last equation. This is the time-independent equation. The equation doesn't have time in it. I guess this is a bit confusing. Now I want to summarize. So let me put these equations in order. One was this, v equal to v naught plus at. Second one was this. And the third one, I usually use this one, v squared equal to v naught squared plus 2a times delta x. Usually instead of x minus x naught, some people write delta x and make it a little bit easier. Delta x, let me practice delta x. Delta x from this equation is, let me say, 1/2 of v plus v naught times t. So if I use delta x, I would replace this by delta x. And I did this one and say delta x equal to that. I have a little trick to both memorize these and use them in problems. These equations are between 4 different parameters. One is v, one is a, one is t, one is x. I have displacement x and v in general. Let me classify those. One is delta x, one is v, one is t, one is a, and if you want, one is also v naught, but v naught is usually known initial situation. And if you look at this, This has all these except delta x. So this doesn't have delta x, but it has this, and that. This equation has all of them except final velocity. So it has this, not this one, and this and that. This equation has everything except time. So it has this one and this one, not time, and this one. And the last equation has everything except acceleration. So it has this, but not acceleration. Usually we have, if you combine this and that, eliminate V naught, you get another equation, which is similar to this one, delta x is equal to Vt minus 1/2 at squared. And this is everything, it has everything, except it doesn't have the initial velocity. If you ask initial velocity, it is in all of them, except this one. Now, you have these equations for constant acceleration and motion. When motion doesn't have constant acceleration in the time interval from 0 to t, you can't use these equations. You have this list of equations. Every problem that you get, no matter how hard it is, it can be broken down into a simple problem that between these 5 parameters, they give you 3 of them and ask for the 4th one. And these are 5. All right? So if you always make the list of known and unknown values in the problem, see something is missing there. It's as an unknown. It's not, you don't know it and you don't care about it, you don't want it. Then that equation that doesn't have that parameter solves your problem. It's always the case. So if you set up the problem between initial and final and write down everything you know about initial and final, that leads you to which equation you need to use. The most confusing part of this part is the students don't know which equation to use. But if you do that, it will be a piece of cake. Now we're going to do some examples.